Welcome back to competition theory. And this one now we do get into the theory a little bit more. That is using theoretical equations to model competition behavior. It gets difficult because you have to figure out a way for your simple variable models, mathematical models, to incorporate the interactions and the changes of two different species now and how they affect each other's growth. It's not just one species with its resource, usually a single resource in the models because they're so simple. Sometimes you can get, I'll show you an example of two resource, one species models. But now we're going to look at two species. And when we get really exciting, or when it'll get really exciting, we'll have two resources, two species. And that opens up some interesting interactions that allow for coexistence. The reason this entire planet isn't colonized by one species that has outcompeted everything else is because there's things that happen. There are multiple resources, there are disturbance, and I'm going to describe that through the rest of the chapter here, or the lectures. Okay, so we ended the last one on the idea of C4, complete competitors cannot coexist, and I'm going to show you a nice Petri dish example of that, and we come up with a new sort of slogan, phrase, theory, the competitive exclusion principle. And this is a little more palatable to me than the ghost of competition past. This just says that if you put two things together in a limited habitat, on limited resources, more than likely one will beat the other one up and take over. And that can depend on the conditions. So our friend Gauss, he was the one that had the glass wool with paramecium hiding or not. He did these experiments here showing competition between fairly closely related, sort of trophically related paramecia. Two different species, Paramecium aurelia, must have been a gold color, that's what that means, and caudatum, and I won't venture to figure out why that's caudatum. But it's inter-specific competition, it's demonstrating the competitive exclusion principle, and let's walk through it. He had these two paramecia. When grown separately, they had a certain carrying capacity. This one, the Aurelia, could grow up to about 200 total volume of cells in the Petri dish, or in this case, it probably was something like a beaker or something. And then the caudatum does not grow as big in its population under the same resource base. It only gets up to about 150 cells, okay? And when you put them together, caudatum never makes it. It's always Aurelia. I wouldn't say always, never say always, but caudatum outcompetes, Aurelia outcompetes caudatum in most experimental manipulations and under this particular resource regime. So something is happening here. There's competition between the two, and there's exclusion from the system if they're both present from Aurelia and knocking caudatum. There isn't enough resource left for caudatum. Okay, Aurelia is hungry. Okay, so that's sort of a nice example of the competitive exclusion principle. It's happening in the real world too. Hard to model because things get complicated, but so it goes. So we're looking now at interspecific competition. And now we're going to build up that Lotka-Volterra model for competition theory. The following model incorporates interspecific competition. You've seen it. It's the logistic equation. But you have to kind of do it for each one as an intraspecific model. That is, population 1 with subscripts 1, or species 1, I should say, has one logistic equation. And then we have a second one for species 2. It's got its own R rate of increase, it's got its own carrying capacity and population size, all right? So those subscripts are just referring to the two different species. They're still separate. So now we're going to do something, we're going to tweak it and put them together, and it gets exciting. And add a coefficient for the competition. So we're going to add those coefficient terms, alpha for species 1, just by chance, that's just how I do it, and beta for species 2. Those are the two sort of coefficients of competition. They show, the alpha and the beta are showing you how one species affects the other's carrying capacity when it's present. It's going to lower the carrying capacity. There's more mouths to feed, but it does it in its own unique way. It's not just adding more of the species that was already present, it's actually adding maybe something that's more competitive, that takes even more of the resource than the species does itself. So that's where it starts to get, I think, starts to get quite interesting. And so now we can take those original equations. By the way, this should not be a subscript. Sorry, that popped into its subscript, but it should be at the level of the regular size in both cases. Okay, so now we add that effect of our competition coefficients. So for species 1, okay, R1 equals N1, and this factor here, that is the carrying capacity factor, becomes 1 minus the population 1 plus the effect of competition of population 2 in that system on population 1's carrying capacity, right? So it's species 1, it's a negative effect, it's getting crowded, it's reaching carrying capacity potentially, or overshooting or whatever, but then you're adding even more problems, that is competition from species 2. And it's not just numbers, so you don't just put N2, you have to have that coefficient of competition, if you will. All right, and then the same thing goes on with species 2. All right, so we're looking at this portion of these figures, of these equations. That's what this is, right? It's still R2 times N2, but then instead of 1 minus N2 divided by K2, it's 1 minus N2 plus beta N1 divided by K2, right? You can walk through that. And again, alpha is the effective competition of species 2 on species 1 carrying capacity, whoops, over here. And then the opposite is true for the other equation, the effective competition from species 1 on species 2 carrying capacity. Okay, you can walk through all that, make sure it is internalized and you can see that. I don't expect you to have the equation necessarily memorized and be able to write it out for this class. When you get to a population ecology class or a class that starts to dig into the population dynamics more so, then you will need to. But for my purposes, what I want you to do is to be able to tell me on a quiz, what is R? Intrinsic rate of increase. What is N? The number of the individuals in the population. What's 1? Species 1 in this case. What's K? Etc. What's alpha? What's beta? You need to know those variables, and in addition to knowing what they are, understand what happens if the beta term gets really big. That means species 1 is very competitive against species 2 potentially. Or if it's really small, then species 2 hardly notices it maybe. Okay, so these are the kinds of things you need to think about. Here's a way to help understand it, maybe. This is from your book. I don't have the figure number. I do have that this is panel A and this is panel B, but there's a figure number also, figure blah, 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 16 point something A, 16 point something B, and there'll be a C and a D. Okay, so here we're looking at vector diagrams from the Lotka-Volterra equations. In the yellow region, both species are doing okay. So on the X is our species 1. And the population of species 1 is quite low in the yellow and is increasing through time, and that's why that arrow points to the right. The population is getting bigger. There are enough resources and not enough competition, either from itself or from the other species, to hinder growth, and so its arrow is moving to the right. At the same time, species 2 is increasing and the arrow is moving up in the yellow zone. All right? And then the generalized, those are like thin arrows. The thicker arrow is sort of a general, everything's moving diagonally towards the blue. Look at the green. Okay, it's the opposite. There are too many mouths to feed. So species 1 is moving to the left. Its population, its numbers are going down because it's not doing very well. Okay, so you're getting fewer and fewer individuals in the green zone, and fewer of species 1 moving left on the x-axis, and species 2, fewer and fewer individuals of species 2, so it's moving down on the y-axis. And again, there's a generalized sort of thicker arrow here to tell you that everything's moving towards this green line. So sticking with the green line, this is the zero net isocline, where the population doesn't increase or decrease. If you pop over here, the population would increase. Okay? If you pop it over here, everything decreases. Okay? But in this case, the way these numbers were basically hypothetically set up, everything is moving down. Oh, in the blue area, you could see that species 1 is winning. It's moving to the right. Its populations are going up with the resource base and in the face of competition with species 2, but species 2 is not doing well. And so everything is moving down to the right. This is where the competition is really getting keen, and only one species in this scenario is winning. And everything is moving down to the right. It eventually hits to a 0 for population 2, and population 1 continues to grow until this sweet spot right there, and that's the equilibrium point for that species. So a lot of words I just threw out there, and you can go back and look at it. Panel A, species 1 wins the competition because it lives on resource levels too low to support species 2, 1 equilibrium point at K1, the carrying capacity for species 1. Competition's too high up here. It draws the population of species 2 down, competition from species 1, until it eventually reaches 0 for population 2. That is all the way down the y-axis. And then population 1 continues to grow until it hits here. It might pop over here, but then it's going to knock back down. It overshoots capacity, carrying capacity, but then it comes back to this equilibrium point. I won't walk you through panel B, but it's the opposite. The thing is, now, in this scenario, population species 2 wins. Again, competition for species 2 knocks population 1 back. That's why this arrow is moving back in this blue zone. But species 2 is doing quite well. In theory, the vector's up, and it's always going to keep going back until it hits the y-axis, where there's no more of population 1. It's at 0, but population 2 continues to grow to its equilibrium point. Simple, right? That's so straightforward. Okay. Here are some interesting, even more interesting graphics. Okay, note here the lines are parallel. The zero net growth lines are parallel to each other of the two species. Now they cross over. And one of these is really interesting because it predicts coexistence. Not panel C, not this one. All right. So we're still looking at, in the gray or green, both species are going down. Their numbers are going down. There's not enough resource to support either one. So species 2 is dropping. Species 1, moving to the left, is dropping. Over here, they're both going up in the yellow. Okay, species 2, going up. Species 1 moving to the right. In the blue, again, is where the competition is happening. And depending on the initial conditions, If you pop out in this blue zone, species 2 is falling, species 1 is increasing, and you're going to wind up at species 1 carrying capacity. Okay? And the opposite is true here. You're going to wind up carrying capacity for species 2. Again, it's because of the coefficient of competition and their interaction with the other species. This site, right in the middle, is not stable. So even if it were to show up there with the population numbers of the two species, very quickly something would knock it off into this zone, this zone, this zone, or this zone, and eventually you'd wind up at either K1 or K2 with the winner of the competition. So either species 1 or 2 wins depending on the initial conditions. And in panel D, coexistence is predicted because interspecific is relatively strong. Interspecific competition. Out here, the competition from species 2 on species 1 knocks back species 1 to this zone here, K1. And the same thing's going on here, knocking back species 2 back to its carrying capacity here. And so all roads lead to this equilibrium point right here. All right? Both species, well, here species 2 is dropping, species 1 is increasing, and you wind up here. Here, species 1 is failing or falling, species 2 is increasing, and you wind up here. Here, both are failing, and you wind up here, or here and then wind up there, or here and then wind up here. And then this one, they're both increasing, but they're going to get there eventually. If they pop out here, the interactions between them through competition, in both cases, push it towards this equilibrium, stable equilibrium point right in the middle. All right? Lots of verbiage in the book, lots of verbiage out of my mouth just now. I hope you can, okay, oh, that was out of order. There's K1, K2. Depending on initial conditions, one of the other species wins. Even though their near zero net isocline lines are crossed, depending on the initial conditions, you wind up with either one species, species 1, or the other, species 2, winning. And then here, what? There it is. You get species, both species coexisting. That's really intriguing for ecologists. That's really intriguing because we know there's a lot of species out there, right? And we know they're, quote, coexisting. They're not sharing a lot of things with each other. That's very non-Darwinian. They're all in it for themselves, but they do coexist, right? There are a lot of woodpecker species in my backyard. Today's my backyard lecture, I guess. Right, I've got some what I believe to be nuttalls and ladderback woodpeckers. I've got the red, but what do they call it? The red belly. I've seen the red head. I've certainly got pileated. A lot of woodpeckers back there. And they're all kind of at the same trophic level of insects, right? So yet they coexist. We'll look at that a little bit more, why that can happen. Look at that tropical reef there. There are a lot of fish. Boy, if you've never snorkeled, you don't have to scuba dive to see an image like this. You could just snorkel, get used to breathing with those snorkels and just kind of get a mask on and find some shallow water location that has so many fish like that. Don't bait for them because that just throws the system out of whack. Just find a place that's relatively pristine, hopefully. Anyway, that's really intriguing for us. Why is there so much coexistence? And why can't we model it very effectively beyond two species, two resources? Well, one resource that we've looked at so far. Let me develop that a little bit more. Liebig's barrel. Remember Liebig's law of the minimum? There's one limiting factor, let's say an element, let's say magnesium, sulfur, potassium, nitrogen, carbon. If it's in limiting supply, that's what's going to limit the population growth for that species. But elements aren't out there in isolation. organisms aren't looking for a single element and calling it good. They're looking for everything. You take multivitamins and minerals in your little tablets if you do. You eat things for the protein. Actually, you're eating things for the amino acids. One batch, actually a complete protein, all your amino acids are in a chunk of meat. Some of those amino acids are in legumes. Some of those amino acids are in, what's the other one? Grains. Neither have both. So you have to add a tortilla to your beans or peanut butter to your sandwich bread. And then you get the complete protein. Anyway, we're all going after all sorts of different things. It's not in isolation. And Liebig's barrel, that's where Liebig's law of the minimum has sort of morphed into now. And that barrel shows you what are called, I think, stays, pieces of wood that keep the water in, all right? And the level of that water tells you how many species. That's kind of a analogy for how many species that system can hold. And in this case, it looks like phosphate, P2O4, is limiting. And so the plants can't get enough phosphate to support much more than what you see there, and the water is running out at the low level of the phosphate. If phosphate became replenished, the next one might be nitrogen over here, or that looks like calcium, potassium, sulfur. These are all low. So these look like the next categories, the next potential limiting resources in this system, right? But right now it's phosphate, and the plants can't get any more populated than what that phosphate allows. The thing is that it doesn't just occur in isolation, as I said. So imagine each organism is a community being limited by a different resource, and the limitations shift through time, as I was just describing. Start with phosphate today, it could be nitrogen over here tomorrow, calcium in a year, maybe in that little tiny location you've got phosphate. A deer comes along and takes a leak, drops some urine. You get nitrogen and phosphate, I believe. Certainly get nitrogen. Maybe it's a carcass, and the bone, which has a lot of phosphate, then replenishes the phosphorus level, and you've got nitrogen, and now the limiting factor is sulfur or calcium or magnesium. So it shifts through time, right? This allows multiple species to coexist, with one species being able to outcompete the others briefly, but not for long. It might be really good at getting phosphorus when it's limited, but given enough time, it loses, either because phosphorus becomes more abundant or another species moves in that's even better than it is, all right? And then it shifts to those that are really good at getting nitrogen or magnesium. So now we think of all of these Liebig law of the minimums as actually multiple element limitations. And they've, very curious spelling there, let's just say we have expanded the Liebig's ideas into a barrel with multiple elements limiting, and you don't have light in there, and you don't have water for plants, but you could also create one of those for animals, for those of you that are more zoologically inclined. And each board in that barrel is a different element, and they are shifting, going up and down in terms of their limitations through the years. That's going to drive coexistence, because no one species wins for long, okay, as I've said in the third bullet right here. So I hope that makes sense. It does draw some interesting lessons with respect to competition theory. Okay. So let me draw this out just a little bit further with a couple more fancy figures. Let's look at one species with two resources. And then we're going to go to two species with two resources. And again, the idea here is we're moving towards coexistence. We know coexistence occurs. We know the simplified Lotka-Volterra models don't support that it occurs. One should always win. Or you have a very stable central point, like in that panel D in a couple of figures ago, but it's so limited. The equilibrium point is such an exact spot that things can't stick on that one little spot for long. They got to pop off and things are moving around, and that opens up a lot of dynamic interactions. Bottom line though, coexistence is out there. I don't think that's the only reason why, okay, that central point is so ephemeral, if you will. It's never long lasting. Mathematically, it's a beautiful, simple result, conclusion, but it ain't very real. So we add new things, 2 resources and eventually two new species. So here's one that I drew up myself for this part of the lecture. We have 2 resources, resource 1 and resource 2. And resource 1, the critical level is right here for this species. Okay, we're dealing with a single species now. And the critical level for resource 2, so this might be nitrogen and this might be phosphorus, that's up here on the y-axis. Okay, and these are zero net growth isoclines, sometimes called ZNGs, zero net growth isoclines. If you're up here, the combination of resource levels, you have plenty and the population will increase. You have enough of resource 1 on the x-axis up here, and you have enough of resource 2 on the y-axis over here, so the species is happy in this zone and it will grow, the population will grow. You can imagine that here it's bad, because now you've crossed over that zero net isocline for resource 1 and there's not enough resource, and so your population will start to drop and move to the left. Okay. Same thing over here, you've crossed the isocline and the population will drop because you don't have enough of resource 2 and the population declines. Okay. And if you're here, that's really bad. You don't have enough of either one. All right. So very simple. Now add a second species and things get kind of interesting. So here's a simple version of what could happen. We still have 2 resources and 2 species, okay? But they're parallel, just like in that, I'll go back a couple figures, sorry, bear with me. You'll have to bear with me too, right there. They're essentially parallel, okay? Right? They're not crossing. So you could see where this is headed. Okay, now we're going to add that second species with the 2 resources. And actually we've already done that, but what's happening now is that each species has honed in on becoming an expert for one of the resources. Okay, and that leads to coexistence. That's in zone 4 here. So there is this overlap of the ZNGs, zero net growth isoclines, okay? And the resources are X and Y, but here both species can coexist. There's enough resources of X, enough resource of Y for species A to survive. It's over in this zone for its zero net growth, and same for the other, for resource Y. So resource X has enough, it's up in here. Resource Y, there's enough, it's over on the right side of the Y resource on the x-axis. They shouldn't have used X and Y, but they did. Here, actually, B wins. It's got enough of both X and Y resource, but A does not have enough. We've dropped below what A needs for resource X. And so when you get down into here, Y continues to thrive, B continues to thrive, but A now loses in the competition. The interesting, you can kind of map that out. I'll come back and give it another version in a review, but 4 is where it's really interesting, because as X gets drawn down, A starts to suffer, B starts to increase, but then B starts to use up the other element or resource and draws it down because it's becoming too populated, and therefore the other species can now take back over, and it just kind of fluctuates back and forth in this coexistence zone, even popping out but then coming back. And we're not going to go into showing the vectors and all that. it gets pretty complicated. But that's the notion. And we're still incredibly simple in my mind. I find it incredibly frustrating because we're only looking at two species with two resources. That's not what's going on out in the real world. But as we described earlier, Hal and Watson still can't model this. We can add a lot. We can add a lot, make it incredibly complicated, but let's not go there. By the way, so here, species A draws the resource down into zone 2. That makes it unavailable for species B, right? Just cross species B isocline for that resource. That is the resource of Y, whatever that is. And the same thing would happen over here, and species B would win, only this time it's resource X that's being drawn down below what A needs, and so B wins. And then finally, coexistence, the sweet spot here at zone 4. Finally, to wrap things up here for today's lecture, there are some real-world, well, Petri dish real-world examples. Two species can be set up to coexist with the right levels of two nutrients. Now, it's just not just the two nutrients, but you have to have the right levels to support coexistence. So here we're looking at a ratio of silica to phosphorus in diatoms, for diatoms. And cyclotella will win when that ratio is 0.6. That is 0.6 Si to P, all right? So there's, well, we'll look at some comparison ratios in a minute, and you'll see how that number works. But point is here that cyclotella does better when there's more phosphorus. I think it's more phosphorus. And then if there's a lot more silica, and now that ratio is 455, then Astrionella, this star-like diatom, does quite a bit better. In fact, wins the competition, and cyclotella loses. Here, cyclotella wins, and it looks like the Astrionella is destined to lose. All a function of these ratios. If you have a lot of silica, this one wins. If you don't have as much, this one wins. But there's a sweet spot. And it turned out to be about 38 silica to phosphorus units. And then both survive and continue to coexist out 40, 45 days. So it's not just having the two nutrients in the species that can utilize both, but it is having the right amounts to find that sweet spot. Okay. By the way, if this stuff sounds interesting to you and you have an aquatic interest, Kim Schultz is a researcher that is very intrigued with these sort of food web dynamics and in aquatic systems. I recommend taking a class with her. Okay, that's it for today's competition, or this segment, and we'll come back to one last segment for this chapter next time. So we'll see you then. Cheers.